Physics 2211 Lab 2, Motion of a Falling Object. Here we go. So, the purpose of this lab is to demonstrate a real-life application of Newton's second law, which I will talk more about in the procedure slide. We will find out, though, that the computational model that took both gravity and drag forces into account was closer to the observed motion than the model that only took gravity into account. We will record the observed motion using tracker software, and we will develop computational models for the predicted motions with gravity and drag force using GlowScript. And the object of choice is none other than Yankee Man. There he goes. Okay, so Newton's second law, the physics properties. So Newton's second law states that the net force is the change in momentum over the change in time, and when you derive that equation, it becomes mass times acceleration equals net force. So we'll use that on the next few bullet points, where the computational model that considers gravity only, the net force is mg. And the computational model that considers gravity and drag forces is net force equals mg minus b, or the proportionality constant, times absolute value of velocity squared. And bv squared is in the negative direction because it is a resistive force that opposes the motion of an object through a fluid, in this case the air. And since mg is acting in the direction of motion, the bv squared is the resistive force, so it's negative. And at some time t, the object will reach a terminal velocity, so that's when the net force basically equals 0, since the gravitational force and the drag forces cancel each other out. And so eventually the terminal velocity, or the velocity of the object, will plateau to the terminal velocity, since this net force becomes 0 and this whole thing becomes 0. So the system is Yankee Man, and the surroundings are the earth and the air. So the procedure, like I said, number 1, we'll record Yankee Man's crash landing starting from rest at some height. Then we'll use tracker software to track Yankee Man's position and time values using frame-by-frame analysis. Then we'll develop 2 computational models on GlowScript that use the same observed conditions. Comp model G considers gravity only. Comp model G plus D considers gravity and drag forces. And finally, we will graphically compare the observed motion with both computational models. So this is the video of the real-time observed position using tracker software of Yankee Man. This is the calibrated point of 0.230 meters, and this is the coordinate axis starting at 0 meters at the 12th frame. So we find out that it takes 0.400 seconds to go from 0.752 meters to the ground. And we'll use those numbers right here in the computational model for gravity only. So we found out that the mass of the ball mass of Yankee Man is 0.05 kilograms. The initial position is 0.752 meters in the j-hat vector direction. The initial velocity, however, is still 0. The B proportionality constant is 0, since we are only considering gravity in this case, not air resistance. While t is less than 0.400 seconds, since that's the time we found it took for Yankee Man to hit the ground from the initial height, we find that the net force is equal to negative m times g, which we derived earlier. And then we update the ball velocity, since ball velocity is v plus at, and a being the net force divided by mass. And this is a linear line, since g doesn't change, and net force is equal to mg, so yeah. But when we consider both the gravity and drag forces, now we include the proportionality constant. These initial conditions stay the same, and we have that the mg is still the same thing, but now we have a drag force, and the drag force is b times v squared. And when the net force is equal to the mg plus drag force, we now get this. So the velocity is starting to plateau more instead of being a linear line, because it wouldn't be a linear line in real life, because of an object can't just get more and more fast in one direction, or speed up in one direction, or else it'd have infinite velocity, which is not right. So when we look at the graphs of the observed position, we can see that the blue real-time position is much more closely modeled and accurately modeled by the yellow line, which is the model of gravity and drag force, while the red one is more inaccurate. So potential sources of error, the tracking inaccuracy for Yankee Man's frame-by-frame position, since I have to manually input the tracking positions. And outside forces like the AC draft could have been unaccounted for. So, which models, if any, predict a terminal velocity? The answer would be the model of gravity and drag, since it starts to plateau, and when it plateaus at some velocity, that is the terminal velocity. And last question: how would the terminal velocity differ if it was thrown downward than from being rest? Well, it wouldn't change in magnitude, but it would be reached more quickly.